Hello everyone. Today we have a new video. Well, this is video 3 in the series on Newtonian gravitational force. In this video, we're gonna solve a problem to find the gravitational field due to a solid sphere. Before we start with this video, please go back and watch video number 1 and video number 2, because that will guarantee a smooth understanding of this new video. Now, assuming you did that, let's start this new video. Just to remind you, the Newtonian gravitational law is saying that the magnitude of the attractive gravitational force between two masses depends on a constant called the gravitational universal constant times the two masses multiplied by each other divided by the distance square. And this expression in its original form is valid for point masses, that is for small size masses. So now, the question we are trying to solve is the following. Find the gravitational potential and gravitational field strength due to a solid sphere of radius r and of uniform mass density, let's call it rho, everywhere outside and inside the sphere. So let's start. So if you have a point mass, and think of this mass as generating a potential field called V. V is equal to minus capital G times the mass that's creating the field divided by r. Now here we are assuming that the point mass is located at the origin. So at any location in space, a distance r from the origin, that will be the gravitational potential field. Also, we have another vector field called G vector, which is called the gravitational field strength. Now this is a vector field which is equal in magnitude to, again, the constant G times the mass producing this field divided by r square, and the direction is minus r unit vector to denote that this is an attractive gravitational field. So let's start the problem. So we have a solid sphere of radius capital R, and we want to calculate the potential of gravity, the gravitational potential. Let's start with outside the sphere. So let's now, because this sphere has a uniform mass density, so similar to the last video, we have what's called a spherical symmetry, which means doesn't matter what location you are around the sphere, as long as you are at the same distance from the origin, the physical quantities should be similar, should be identical. So the gravitational field V should be a function of r only, of distance. It should not depend on the angles in spherical coordinates, the angle theta and the angle phi, because of this spherical symmetry. So, because the location is not relevant to the problem, I would choose a point on the z-axis to make things easier for the mathematics. So I'm picking a point on the z-axis at a distance called z0. And this z0 here is drawn outside the sphere. Now we can take it even inside, doesn't matter. Later you can see the difference when we try to solve this problem. What's the difference between being inside or outside the sphere? So for now, I'm just choosing the point to be outside the sphere, located on the z-axis. Now we cannot use directly the gravitational law to calculate the potential at point z0, because again, the gravitational law is valid for point masses. So what should we do then? So now we take the sphere and we cut it into very small pieces, for tiny pieces, infinitesimal pieces. Each piece carries a volume, a small volume. Now we can think of these pieces as point masses, and now we can calculate the small potential due to one of these pieces. And later we're going to add, or in a different way, we integrate over all pieces, which means we're going to integrate over the whole pieces of the sphere. So let's start writing notations. So the point z0, which is I'm taking on the z-axis, can be written in vector form as z0, that's the magnitude, times k unit vector, because it's along the z-axis. Now let's take a small piece of the sphere located at distance r. And so if I want to write this piece or this location as a vector, so I will say r vector equal r, the magnitude, times r unit vector. And remember that because this is a solid sphere, so r small can be anywhere between 0 and capital R, which is the radius of the whole sphere. So because we are inside the sphere. So now, if you think about this small blue volume that I'm drawing, now this small mass is producing a gravitational field at point z0. And if you watch video number 2, you know that the small potential produced by this small mass is minus the constant g times the small mass of the blue piece divided by the distance between this small mass and the point z0. So the mass of the small blue piece is equal to the density, the mass density, times the small element of volume. Now we know that in spherical coordinates, the element of volume is equal to r squared sine theta dr d theta d phi. So now we know how to write the small mass of the blue piece. What about the distance? If you watch video number 1 and video number 2, so you know that the distance between the blue piece and z0, which is the length of the red vector, can be written as the square root of the quantity you see in the last line. So now we're gonna put everything in the small element of potential, gravitational potential, and then we're gonna add all pieces so that we're gonna integrate over the whole sphere. So now the total gravitational potential V is equal to the integration you see in this page. Now G is a constant with a minus sign. I took it outside of the integral, and also because we are assuming the mass density to be constant, uniform, so it's also a constant that I took out of the integration. So what I am left now with a triple integral, because this is integration over the volume now of the sphere. Now you can see that the numerator is just the element of volume in spherical coordinates divided by the distance, the length of the red vector. Now here in the integration, in the limits, I only put the limits of the angle phi because I'm going to start with this integration. It's a very simple integration. You can see in the integral, there's nothing depends on the angle phi, and so the integration over phi is so simple, it will just give you a factor of 2 pi. After we finish the integration of phi, I'm going to do the integration over theta. Now the integration over theta is not difficult. It's also easy. It can be done by substitution, and you can watch video number 2 to see this point again. Now the limits of integration for theta starting from 0 and going up to pi. So by integrating by substitution, we find the answer of V, and we are left with one integral over R. So you can see now what is the answer. The answer is there's some constant, and then we are left with an integration over R, and R is starting from 0, the smallest from the origin, until you reach the capital R, which is the radius of the big mass or sphere. So finally, we have just to find out what is this integral to finalize and finish the problem. Now again, similar to video number 2, you have to be very careful now with this integral. We have a square root of a quantity squared. So now many students will simply, without being careful, will just say square root of something squared, you just drop the square root and the square, and they are left with the quantity inside. That's not always true. You have to be very careful. As we explained before, the square root of a quantity squared is equal to the absolute value of what is inside the square root. So the first quantity is easy to find. The square root of r plus z0 all squared. Now r is positive, we know that, and z0 is positive, so the sum is positive, and so yes, here I can drop the square root with the square, and we are left with r plus z0. Now the problem is in the second quantity. So what is the, if you look at the last line, what is the square root of r minus z0 all squared? Now here is what distinguishes between being outside the sphere or being inside the sphere, and where are you exactly inside the sphere. So let's start with outside, being outside the sphere. Now remember, if you are outside the sphere, then we know that, of course, small r will always start from 0 and will finish with capital R. However, z0, because you are outside the sphere, so z0 is always bigger than capital R. So now if you think about the square root of this quantity, this now you should get the absolute value. The absolute value is the bigger, which is z0, which is because you are outside, minus small r. So that's the value of the square root of r minus z0 all squared. So now because now we already determined what is this square root, I can go back to the integral, substitute this, and then do the final integration, which is very simple, and you can find the answer easily. Now we know what is the volume of a sphere, so I'm going to substitute for the volume of the sphere, multiply by the density, which will give you the total mass of the sphere, and you finally find out what is the potential due to the sphere, and voila, the gravitational potential now you can find it's equal to minus capital G, the total mass of the sphere divided by z0. Now this is for outside the sphere. Now because z0 was just an arbitrary point I took, now I can just remove z0 and replace it by a general point in general, so I can use the symbol r. So now the gravitational potential outside the sphere is written more generally as minus capital G, the mass over r. And what you notice is that if you are outside the solid sphere, then the gravitational potential is exactly as a point mass. So if you are outside the sphere, you would think, or I mean the answer exactly similar to as if the mass, the big mass, is nothing but just a point mass located at the origin. And because this is the gravitational potential, now you can calculate the gravitational field strength, and it's again similar to a point mass. So the conclusion is, if you are outside a solid sphere of uniform mass density, then the answer is exactly as if the sphere was a point mass located at the origin. Let's just make one remark about this case. Now in this problem, we assume that density was uniform, was constant. So now what happens if the density is not constant? But let's say the density depends on the radius or on the distance r. Now in this case, you can prove that the answer is still the same. The same conclusion will hold. So again, the gravitational potential will exactly have the same form. So it doesn't matter if the density is uniform or the density is a function of r only, then you will get the same conclusion. However, if the density depends on the other two angles, like theta and phi, then the conclusion will not hold anymore, because you are breaking the spherical symmetry. And so our conclusion is not correct. Of course, this is not an interesting case, and we are really, what is more interesting is the first remark. Because, for example, if you think about Earth, now Earth, think of it as almost like a sphere. Now we know that the density of Earth is not constant, is not uniform. However, to a very degree of accuracy, the mass density depends on the radius. If you are close to the origin or to the center of Earth, that's where the core is. And once you are moving away, then the density is changing, but it is, to some extent, it's a function of r. So the conclusion will still hold for a spherical solid mass of density that depends on the distance r. Now let's go back to the other case where you are inside the sphere. So up to now, okay, this integral that we found still holds. Everything so far, just you follow the same steps until you reach this integral. Now the difference between outside and inside really is just coming from the square root, to simplify the square root. And that's it. So the first square root is similar to the previous case. Now let's think about the second square root. So what is the value of the square root of r minus z0 all square? Now here, just think a little bit to understand this. Now we are inside the sphere. So this means z0 is less than capital R because we are inside the sphere. Now for r, for small r, then that's again, it will vary between 0 and capital R, the radius of the sphere. So now, if you think about it, because we are integrating over small r, so there are two regions inside. The first region is where small r is greater than 0, but it is less than z0, and z0 is some point fixed inside the sphere. And the other region is where small r is more than z0, but it is less than capital R, the radius of the sphere. So the two cases are different, and they will lead to a different value for the square root. For the first case, the square root will be simplified as the bigger quantity, which is z0, minus a small r. While for the other region, the bigger quantity is small r, and the smaller will be z0. So you can see the difference now. So the integral really over r now will split into two integrals. The first integral will be from small r equal to 0 to z0, and the second integral will start from r equals z0 to capital R. So you can see that now the integral is easier to perform. You can do that and you can substitute, and I will give you just the final answer. So you can prove that the potential, gravitational potential, while you are inside the sphere is equal to, I can see it's just minus capital G mass divided by capital R times the bracket. And the bracket, what's inside the bracket? 3 over 2 minus z0 square divided by 2, the radius of the sphere square. So that's the answer. Now the conclusion is, so far, the answer is different from outside. So inside the sphere will not give you the same answer as if you are outside. And you can see that if you are inside the sphere, the gravitational potential is not similar to a point, to the effect of a point mass. In fact, you can see that the potential depends on z0. So this means it depends on where you are inside the sphere. Now, because z0 is just an arbitrary point inside, I will just replace it by small r, and in general, I will write the potential as shown in the second line. And remember, this is for inside the sphere. Now you can check what happened at the radius of the sphere. So when small r is equal to capital R, now you can substitute small r to be big R, and you can prove that the answer will be minus capital G m over r big of the sphere. So that's the the potential, gravitational potential at the surface. Now, what about the gravitational field strength? That's the gradient. Well, if you think about this again, let's go back to potential. So the potential now has two terms. Now, if you think about the first term, it's just a constant. All things in the first term are just constant, while the second term has a dependence on small r. So where are you inside the sphere? So to find the gravitational field strength, we take minus the gradient of the field, the potential field, and we will find that the answer is nothing but a minus with a constant, just a constant that I will call k, for simplicity, times r vector. So we have here r and r unit vector. Now together they will make r vector. So that's the gravitational field inside a sphere. And if you think about this, that's an interesting conclusion, because this resembles the simple harmonic force. So if you are inside a sphere, a solid sphere, gravity will behave exactly as a simple harmonic force. It is equal to minus a constant times the vector, location vector, or the position vector r. So this means, if, let's imagine there's a hole digged throughout Earth and there's a particle falling. So what's going to happen, that this mass will, the small mass will fall according to a simple harmonic motion. So it will fall down, gaining speed as it falls down until it reaches the origin. Now once it reaches the origin, it won't stop, of course, because it will have kinetic energy, momentum also, and it will keep moving to the other side of Earth until it reaches the other side. And then it will come back and start oscillating all the time. So this will be an oscillational motion, simple to a simple harmonic force. I hope you understand this part. This is an interesting part, and we will see you in a different video.